Ta-da. And we have victory. Michael, thank you.
Thank you. All right, good morning. So I have the pleasure of being the first here today this morning. As I was introduced, my name is Mikael Holmberg, and I'm coming from Extreme Networks. So I'm going to talk about a topic that might be a bit outside of what you guys usually hear on this event, which is obviously covering things like BGP, RPKI, things like that. I'm going to touch on 5G. So now you might wonder, so why is a guy representing an Ethernet switch router vendor talking about 5G? So reason being is that I'm going to touch on the transport part for 5G, and I hope that you basically, after my 30 minutes presentation, get the context why actually somebody representing an Ethernet vendor is talking about 5G and transport in particular. So to set the ground, 5G is much more than just basically radio and core. 5G is things like automation, orchestration, management, virtualization, software-defined infrastructure, and transport. So my thought was to basically, set the stage here for my talk, to kind of start with a recap of 4G and then look at 5G. And I'm doing this in the context of truly transport part. I'm ignoring everything else. I'm just, kind of touching on the transport part. Due to the fact that, 5G is truly driving network changes. And with network, I mean basically going into something called the X-haul networks. Being the legacy, backhaul going into now front-haul, mid-haul, and backhaul. But if we basically start to, look at this from 4G and then kind of comparing that to 5G going forward. So 4G was one key service, one shared transport network. And that shared transport network was basically just backhaul point-to-point connectivity provided by carrier Ethernet. Totally fine. Consumer focused, you had best effort traffic, latency is not critical. And then, you had some statistical SLA for backhaul transport. And you had basically, or have basically, a simple RAN architecture. Now, if you look at 5G, first of all, one key thing with 5G, it's a service-driven architecture, which basically means that you talk about 4 predefined services. You had a RAN 5G core, you have the hyperscalers, as well as transport. And then you go into things like, network isolation, slicing, which basically means that you are going to have the same network, or the same network is going to provide transport for multiple different use cases. So now you start to talk about things like different requirements within the network. So truly, going from best effort to critical data, which basically means that you might have, bandwidth-hungry applications like fixed wireless access, or you might have something that is truly, latency dependent. Many of you have probably heard about the, kind of famous 5G killer application being the autonomous driving, which basically, as you understand, means that you need to have truly low latency. So that gets you into things like how would you cope with latency, QoS, all those different things. And then from previous 4G, you go into 5G, where you basically have then, the multi-destination, multi-point connectivity, dynamic connectivity requirements. So that actually dictates more or less that you start to move now from a layer 2 environment into a layer 3 environment. And then you go into something like the CU to CU. So sorry, there's a lot of acronyms here, but in short, it basically means that you start to talk about, domain-driven things, like the example I gave you on autonomous driving. We all understand that latency is a key, attribute. You can't cope with much latency. Hence, you are going to have traffic, residing within an area so more a domain in that sense. And then you get into the other acronym being MEC, which is obviously edge or you know, the multi-access edge, mobile edge cloud, whatever you basically want to kind of use for that acronym. And as mentioned, routing is required. And then to add more complexity, you go into multiple RAN architectures. And to add on, you start to look at virtualization. So virtualizing the core, the control and the user plane. So I guess you kind of realize that with more or less this introduction, 5G is putting a lot of new demands on transport networks. So I want to touch on this slide just briefly, but basically what I want to get with this one is saying that, as said, you have different RAN architectures. So you have the distributed RAN, which is more like the legacy 4G. This is still going to be applicable for 5G going forward. Then we are going to introduce something called the centralized RAN, or the C-RAN, which is basically an architecture in which the base station is split into two parts. You have your radio head and baseband unit. Taking this now further basically means that you talk about virtualized RAN, which basically is that you are means that you are going to virtualize all your RAN functions. So think of this in a nutshell, that instead of having purpose-built hardware for your radio functions, I'm going to move those radio functions onto running on computes within a data center. So you are basically going to have a complete kind of virtualization of all those functions running on computes. And then you might have heard of the Open RAN, O-RAN. O-RAN is not an architecture per se. It's more like a way of defining a disaggregated model where you basically have multiple different vendors, equipment, software, subsystems, so on and so forth, defined within open interfaces and things like that. So with that said, I'm basically now going to touch more on this virtualized RAN, the vRAN part. So is your network truly prepared for the evolution to 5G? As you can see in the slide here in the middle, you basically have an itself, basically, where latency is becoming truly a critical factor. And then you go into massive, machine-to-machine communication like Industry 4.0, where you basically have a lot of sensors, things like that, where security might become the challenge, how to basically, be able to realize that. So PTP, I guess majority of you guys heard about PTP. I guess many of you might have deployed it already. But PTP in a nutshell, it's a protocol for distributing precise time and frequency over packet networks. It's an IEEE standard, and you basically had the first version ratified back in 2002, which was targeting LAN applications. The second version back in 2008 was expanded to basically cover the telecom networks, and there is a third version now under discussion as well. So for PTP, time is carried in an event message, which is transmitted from a grandmaster clock into a slave clock, which basically means that I have a way of putting a timestamp on my Ethernet packets across the path from my grandmaster all the way to the base station or my radio. It runs over Ethernet and IP networks, and you basically have also an acronym TSN, which is time-sensitive networking. Under this 802.1q umbrella, you basically have the CM part, which is more looking at it from a telecom side, and then you have the BA part, which is more looking at this from an AVB, as well as obviously the aerospace, industry utility, all those different things having a bit different requirements from a timing perspective than in the telco part. And then you have some other, like radio Ethernet, which is a way of transporting the TDM-based CP traffic as blended traffic over an Ethernet connection together with Ethernet. I'm not going to dig into more details on this. This is just kind of an overall, just statement that this is obviously what the TSN is defined as. So to put this into some context, you also have PTP profiles, and in the first version you had a telecom profile for frequency defined as the G8265.1, which was published back in 2010. And the main idea with that profile was to support frequency synchronization over telecom networks. And to basically define what the profile is, it contains a defined combination of options and attributes and values defined within a profile for specific use cases in that sense. To basically we'll fast forward here and look at the current kind of from a 5G point of view, you have two new profiles. You had the G8275.1, which is the full timing support, and you have the G8275.2, which is a partial timing support. In a nutshell, the difference between these two are that the full timing support requires each and every device within your network to be a PTP boundary clock. So PTP have, things like boundary clock, transparent clock, and transparent bridges. It's just the way of how you would then basically regenerate your frequency more or less. But in a nutshell, to understand the difference, so full timing support demands each and every device within your PTP domain to actually support PTP boundary clocks, which obviously is or means you need to have a greenfield installed for that. While the partial or the G8275.2 partial timing support allows you to have either boundary or transparent clock or even transparent bridges within your domain, PTP domain. And to translate that into a more kind of understandable lingo means that not each and every device within that PTP domain need to be PTP understanding. However, having said that, if you look at the last bullet point, you do have a predefined target accuracy of 1.5 microseconds between any grandmaster and your end station. This is, the magic figure you need to work with. So I'm going to skip over this in the interest of time. You guys have this as reference material. And get to this one. So this is basically, just an illustration of your PTP domain as such. So what you'll have on this one is your GNSS satellite providing you the time. You might have, multiple of those for redundancy. Then you have your grandmaster clock, which is basically responsible for picking the time for your GNSS satellite, put it into a packet, and transport it further on over your network. So this is your grandmaster clock, which is basically your reference, your PRTC reference clock here, which basically means that each and every path within your network, going from your grandmaster to the base station or your radios, needs to be PTP enabled, needs to understand PTP. So, as I mentioned, you had 1.5 microseconds as the magic figure here between any, radio and your grandmaster clock here. And then obviously now you see you have a 3 microsecond, but the 3 microsecond is between any two, RUs. And this is a relative measurement. So this is truly, what is defined. So you talk about something like the TAE, which is a timing alignment error, and obviously you need to basically, obey to that one. There's a bunch of other things here, but in the interest of time, I'm going to skip over these and just get into, the key factors and how would you measure this within your network, because I guess you guys at a given time are starting to look at how would you transport 5G traffic within your infrastructure, how would you provide some kind of a path for that. So you get into discussing or looking at the factors that make a poor synchronization. You talk about two things, you have the CTE and the DTE. You have your latency asymmetry and your latency variation. Now, maintaining synchronization quality is basically maintaining your latency. And the right-hand side, you basically have an illustration of PTP. So it's basically the PTP event message flow, which defines the packet time, which is more or less the packet timing signaling, where you basically have the master frequency is more or less then obtained by having the timestamp T1 and T2 together with your sync and sync ACK messages T3 and T4. This is how you would then basically synchronize your slave clocks to your master clock. Oh, sorry for that. There was supposed to be a build on this, but anyways, let's cover this from the bottom up. So the first part is then when you start to measure this and make sure that your network is truly, prepared for 5G transport. As said, is being able to measure your timing alignment error. And you have multiple different kind of aspects within your network. You obviously have the fixed network itself as well as the over air. But on the right hand side you see the max TE, timing alignment error, 1.5 microseconds. That is end to end, as I alluded to earlier on. But then you see the kind of the orange arrow as well, which basically defines the max TE being 1.1 microseconds. And this is over the network, over the wired infrastructure. Which basically means if you look at the left-hand side of the slide, you basically see that, okay, so the first part is that you're going to take your time from your PRTC, basically introducing your timestamp into packets on the grandmaster clock. Then you're going to introduce some kind of alignment error, as we can see 35 nanoseconds here. Then you go into your DTE and the CTE part, one being the dynamic, one being the constant. The constant is basically your network elements. And what is a network element? It's a switch, it's a router. And there you have different classes, A, B, and C, which basically defines what is, the timing element, the timing error that you are going to induce by implementing such a node within your network. So that would dictate how many nodes you can actually have in your network. So as we can see here, you have a type A being 50 nanoseconds, type B being 20 nanoseconds. In addition to that, you are going to add on your link asymmetry delays, which is basically your link delays, latency. And there we can see you once again have, depending on the type of the node, different values. So all in all, 1.1 microseconds is the network-wide timing alignment error that you can cope with. And then you add in, the end application noise and some rearrangements of short-term holdover, things like that, which is RF over air. And this brings you to the total value of 1.5 microseconds. So on that note, this was a pretty fast walkthrough, touching on the transport part for 5G. Might be a lot of abstract things for you guys, but I think, the key thing is to understand that 5G is putting a lot of new requirements on your network infrastructure going forward. Any questions? Did you follow me on my presentation?
All right. Well, anybody else, any questions or any comments, follow-ups? Please announce your name and company.
Thanks, morning. I'm Kim from Dutch Cooking. We are the Wi-Fi sponsor for the event, so I don't think there have been any issues. And I also just wanted to let you know that we are a distributor for Extreme Groups. So between Mikael and I, if you want some more information, please reach out and I will be around.
Thank you.
Great. Thank you, Michael.
All right, thank you.
All right. So I think up next is Mark.
Let me put your mic. And close. Yeah.